Hello, welcome back to Basics of Finite Element Analysis Part 2. Today is the last day of this week, which is the 7th week, and what we will do today is we will actually calculate this Jacobian matrix and also the transformations for 3 specific elements, and we will learn a little bit more about the conditions required for having valid transformations. So, what we had shown in the last class was that we have to express, if we have to express partial derivatives of psi functions, which are interpolation functions for primary variable, in terms of their partial derivatives in terms of x and y, then we have to compute the inverse of Jacobian matrix, which is J star, and multiply that matrix with partial derivatives of psi with respect to zeta and eta. This is what. Now, for this inversion to happen, we have to, if I have to invert a matrix, then what should be the requirement for that matrix? So, if J has to be inverted, then J should be non-singular. This is very important. What does that mean? What that means is that its determinant should be non-zero. Okay, its determinant should be non-zero. And another thing, this J matrix exists at which point in the element? So, this is all happening at element level. In this entire discussion, we have not put superscript E, but all this description is in context of calculating Kij for eth element. So, all this is happening for eth element. Now, the elements of J matrix, del x over del zeta, del y over del zeta, del x over del eta, and so on and so forth, they are at what locations are we calculating these derivatives? We are calculating them at all the points in a specific element, because we are trying to find out Kij for eth element. So, at each point in the element, so suppose I have a rectangular element or a quadrilateral, there is some point P, at each point there will be a differential of del x over del zeta, del y over del zeta, and so on and so forth. So, all these terms in this equation, they exist at every point in the thing. So, if J has to be non-singular, at which point should it be non-singular? It should be non-singular at all points in the domain. So, it should be non-singular at all points in eth element. And a condition for that to happen is that zeta and eta, which are zeta and eta, which are functions of x and y, they should be continuous, differentiable, and invertible. They should be continuous, differentiable, and invertible. So, it has to be non-singular, because if it's not non-singular at all points, then we cannot have this inversion, and then we cannot compute partial derivatives of psi with respect to x and y in terms of their partial derivative in terms of zeta and eta. So, this is important. So, what we will do is we will do an example, or actually 3 quick examples. Okay. So, the first example is an element which looks like this. It is a quadrilateral, I should be able to map it to a square in the zeta eta domain, right. So, here my x, this is my x axis and this is my y axis, and the local coordinates are 1, 2, 3, 4. Okay. So, this is my first domain or first element. We will see whether we can compute for this or not. What are the, to map this, what do I have to know? I have to know the coordinates of this thing. So, the coordinates are 0, 0, 2, 0, 2, 3 and this is 0, 5. Then I will take another element, it looks like this. So, this is also a 4 noded element. So, this is my second element omega 2, and here also I will first. So, whenever we draw an element we have to put its node numbers very clearly. So, this is node 1, 2, 3 and 4, and the coordinates are 2, 0, 3, 2, 5, 3 and 2, 3. So, what I will suggest is when you revise this, you actually make this element with in actual dimensions with these coordinates, and you will see that the shape looks something like this. Okay. So, this is important to understand. The third case, so this is omega 2, so this is case 1, this is case 2, and then we will also have case 3. And what is case 3? Geometry same as case 1, but nodes reversed. Nodes are reversed. So, what are the reversed nodes? So, I start. So, here I in the original case 1 I was going 1, 2, 3, 4 anticlockwise. Here I will do 1, 2, 3 and 4. Okay. So, here my node numbers are in red. Okay. And in all these 3 cases I have to map these into zeta eta coordinate system where the shape of the element is square, size is 2. So, in all these 3 cases the master element will be the same. So, what is the master element? This is there, and I will also mark the node numbers 1, 2, 3, 4. So, the node numbers do not change, size of the element does not change, the coordinate system does not change for the master element, it is fixed, it does not change. Okay. So, our aim, what do we want? We want to see whether we can invert these things correctly or not. So, our aim is, if I have to invert it, if I have to compute this, I have to make sure that the Jacobian matrix is non-singular, right. So, we will see whether the Jacobian matrix is non-singular for all these 3 cases or not. So, find J for all cases. Okay. So, to find J, what do we have to do? We have to find these parameters del x over del zeta, del y over del zeta, right. So, what does that mean? I have x This is the expression we had developed earlier, right? If I know this expression, then I can compute all those derivatives in the J matrix. In this matrix, I can compute all those derivatives. And psi I hat represents what? What are psi I hats? They are the shape functions. They are also interpolation functions, but in this case they actually specify the shape. So, they are the shape functions which map x and y into the zeta eta domain, and they help us transform an arbitrary quadrilateral into a square. So, these are the shape functions. And what are these shape functions? These shape functions will have a value of 1. Psi 1 will have a psi 1 hat will have a value of 1 at node 1, and it will be 0 at all other locations. So, we had developed these shape functions earlier. We had written expressions. These are the 4 shape functions. So, I do not have to write these 4 shape functions again. So, what I will do is del x over del zeta is equal to 1 by 4 minus x1 So, what is x1? It is the coordinate of the first node. Whatever node we are, whatever element we are dealing with, if we are dealing with this first case 1, then it will be 0. If we are dealing with case 2, it will be 2, right. So, it is the coordinate of first node. So, del x over del zeta is minus x1 into 1 minus zeta plus x2 plus x3 minus x4 okay. Del x over del eta is equal to 1 by 4 minus x1 minus x2 plus x3 plus x4. So, these are the 4 expressions, and how did we get these 4 expressions? We essentially differentiated this relation, these 2 relations, and the expressions for size were given earlier. These are the expressions for size. So, we plugged in these expressions, and x1, x2, x3, x4, y1, y2, y3, y4 correspond to the coordinates of local nodes 1, 2, 3, 4 for any element which we consider. So, these expressions do not change from element to element. The only thing which changes is values of x1, x2, x3, x4, y1, y2, y3, y4. Okay. So, now what we will do is, using these formulas, we will find out the value of Jacobian for each of the 3 cases. So, case 1. x1 equals 0, x2 equals 2, x3 equals 2, x4 equals 0, y1 equals 0, y2 equals 0, y3 equals 3, y4 equals 5. These are the values. How did we get these values? We got it from this picture. Okay. So, what we will do is we will plug in these values in these expressions, and I will write the expression for J matrix, and it comes as 1 minus half into 1 plus eta 0, 2 minus zeta by 2. So, the determinant of J matrix is 2 minus zeta by 2. Okay. Is this 2 minus zeta by 2 always more than 0? Yes, because what is the maximum value of zeta possible? 1. Zeta varies from minus 1 to 1. So, even if it is 1, then the value of this J matrix becomes 1.5. Okay. So, this is always 0, which means that I can validly transform this quadrilateral in case 1 to a master element back and forth, and that transformation is valid and I do not have a problem. Now, let us look at case 2. Okay. Here x1 was 2, x2 is 3, x4 equals 5, x4 equals 2, actually this is x3, and y1 equals 0, y2 equals 2, y3 equals 3, and y4 equals 3. So, the Jacobian matrix becomes eta by 2 plus 1 half 1 minus eta half 1 plus zeta and 1 minus zeta by 2. So, the value of determinant is 3 over 4 into 1 plus eta minus zeta. Is this Jacobian always positive? Can we find at least one single point where it is not positive or not 0? It is not always positive. Actually, it is not always non-zero. We have not talked about positive and negative till so far. For example, even if we find one single point when it is non-zero, then the transformation will not work. Transformation will. Example, when zeta equals 1 and eta equals 0, Jacobian comes to be 0. And we can find several such points actually, right. So, what that means is that I cannot transform this to this and back and forth. This is not valid. Here to here it will work, no problem, but case 2 to case 3 will not work. And then the last case, case 3, again you can put in these different values of x1, x2. So, here the element was same, okay, element was same, but the numbering changed. So, x1 node number 2 changed, node number 3 remained same, but node number 4 changed. Okay. So, the numbering changed. So, in the first case the numbering was anti-clockwise. See, here it was anti-clockwise, and in first case it was also anti-clockwise. In here also it was anti-clockwise, but in third case it was clockwise, right. Clockwise. Numbering was clockwise. So, in your master element it is anti-clockwise, in your actual element it is clockwise. What does that mean? Let us see. X1 is 0, X2 is 0, X3 is equal to 2, X4 is equal to 2, Y1 equals 0, Y2 equals 5, Y3 equals 3, Y4 equals 0. So, the Jacobian is eta 2 minus eta by 2, 1 minus 1 plus zeta by 2. So, its determinant is minus 2 plus eta zeta by 2. Can it be ever 0? What is the maximum value of or minimum value of neta times zeta? Minus 1. See, neta zeta, they vary between minus 1 and plus 1. So, this term at the minimum it will be 2 minus half, which will be 1.5, but there is a negative sign here, right. So, it will always be negative, it will always be negative, and when it is negative, this type of transformation is not desirable. You will get your answer. But what will happen is, at an element level there will not be any problem, but when you do that assembly level, some terms will become negative, some terms will become positive, and the assembly will not be valid. Okay. So, when you are doing these transformations, you have to make sure that the node numbering in each element is consistent. If you are using this anti-clockwise in your master element, in every element it has to be anti-clockwise. So, this is one. Couple of things. So, case 3 we do not like it, because when we have assembly there could be problems. Case 2 is the situation where it is the matrix is not, J matrix is not invertible. So, we cannot compute K matrix, right, and why is it not invertible? In first FEA course we had said, and with this we will close the discussion for today, that the domain should be convex. And what was the definition of convex? That if I have any point, so this is my domain, if I have any point in the system, I should be able to connect these 2 points with a straight line, and the straight line should not go out of the boundary of the element, okay, between any 2 points. So, this is, so in this shape this is a convex domain. This is a convex domain. Now, if I have this is not a convex domain, because if I have to connect these 2 points, I go out of the system. So, for non-convex domains, my Jacobian will not necessarily be non-zero at all points. It will not necessarily be non-zero. Now, in this case, this element, is it convex or non-convex? It is non-convex, because if I connect these 2 points, I have to go out here. Okay. So, essentially what that means is that this angle should never be, all interior angles should never be, so theta should always be less than pi. Okay. If all interior angles in the element are less than pi, then I will have a convex domain. See, here also the angle is more than pi. Here at every point the angle is less than pi. So, J is invertible only for non-convex domains. So, two important things we have learnt, that we have to make sure that our elements should remain convex, and the second thing is that our numbering is important, otherwise at assembly level we will have a problem. Okay, at assembly level we have a problem. So, with this we conclude the discussion for this week, and in the next week we will start developing details on some other problems, and with this we conclude the discussion, and thank you very much and have a great day. Bye.